And another problem would be, what if different patients need different model? We all know that in the medical domain, different patients may actually have very different properties, or even different conditional dependencies. Not to mention that these data sets are often relatively small. So in this case, some machine learning model may not even generalize across different subjects. And this can actually be formulated as a domain adaptation problem. To give you some background, usually domain adaptation refers to the problem of transferring a model from a source domain to a target domain. And typically, we will assume that we have access to the label XS the data XS and label YS in the source domain, and the label and unlabeled data, basically the data XT in the target domain. And the goal is to train a model that will predict the target domain label YT as accurately as possible. And naturally, these can be extended from one-to-one setting to many-to-one or many-to-many settings. But the problem is the current domain adaptation is often categorical. It only considers transferring from one category to another. For example, you may be wanting to adapt from a MNIST dataset to the SVHN dataset, or adapt from an RGB dataset to a DAP dataset. But in the real world, many problems actually involve continuous domains rather than categorical domains. For example, in medical applications, one may usually want to adapt the models across patients of different ages. For example, here, patients of different age can be one domain. And here, age is actually a continuous concept. Another example will be a self-driving car, where we want to adapt models to the environment, which is continuously changing over time. And here, time is a continuous index, and that actually contains a lot of information, right? Traffic conditions, lighting conditions. So it might be good if we can adapt continuously across time. So essentially, traditional categorical domain adaptation only consider adapting across only a handful of domains, and our proposed continuously indexed domain adapts from continuously indexed source domain, which may be infinitely many, to potentially infinitely many continuously indexed target domains, where these domains all often follow a continuous structure or trajectory. To give you some intuition, let's take a look at a toy data set where we have 30 continuously indexed domains, and we color the labels by red and blue. And this is domain 1, domain 2, all the way to domain 15 and 30. The task is, we are given the label data from the source domain, and we want to predict the labels for the rest, basically for all the target domains. And let's take a look at how categorical domain adaptation works. This is one of the categorical domain adaptation methods, ADA, which treats all source domain as one single source and all target domains as one single target, and perform one-step adaptation. We can see that it does not work at all. And this is another categorical domain adaptation method, BANN, a very classical one. Basically, it will split the target domains into smaller parts and perform one-to-many adaptation. It does not work either. So how should we perform continuously indexed domain adaptation? Note that these categorical domain adaptation methods fail because it cannot measure the distance between different domain indexes. For example, they don't know that domain 1 and domain 8 are actually closer, while domain 1 and domain 15 are more distant. Therefore, they cannot capture how the data distribution continuously changes along the domain index. And all they can do is just to blindly transform the data into a common space, which leads to poor performance. And our idea is to take the domain index here as input as well. And hopefully the model can learn to rotate the data distribution according to the domain index. And fortunately, this can be done and implemented easily using an adversarial learning framework. But before going into details of our methods, let's take a look at how traditional and categorical domain adaptation methods work. Usually they will take in the data X to the encoder and just produce some encoding Z. And the predictor F will take in the embedding and predict the labels, while the discriminator will take in this embedding and distinguish between source domain embeddings and target domain embeddings. Different from these categorical domain adaptation methods, in our proposed continuously indexed domain adaptation, or CIDA in short, we're actually taking both the data and the domain index as input and produce the embedding Z. After this, the predictor will remain the same, while the discriminator, instead of doing the classification task to classify between source and target, will just directly predict or regresses the domain index. And naturally, we will have to use a L2 loss between the ground truth and the predicted domain index. And correspondingly, the encoder and predictor will try to fool this discriminator while predicting the label as accurately as possible. Note that this L2 loss is actually crucial so that this whole model can be aware of the distance between different domains, because it introduced a continuously concept into the model. But even doing this, our CIDA still faces another challenge. Let's take a look at the embedding distribution during training. Here we use different color region to represent different embedding from different domains. For example, we have blue to represent domain 1 and green for domain 2 and red for domain 3. And ideally, we want all these domains to be aligned perfectly. And by aligning, I mean that if you look at each of the embedding points, and if you look at the probability of the embedding coming from every domain, it should be the same everywhere. But with some theoretical analysis, we find that the vanilla version of CIDA can only guarantee to match the expectation of the domain index. For example, it may converge to something on the right here. If we look at these 3 embedding points, they actually have the same distribution. They actually have the same expectation, but they have a very different distribution of domain index. And so to alleviate this problem, what we do is that we find that we can actually match the variance as well. And fortunately, we can do this by a simple multiplication of the model. So instead of predicting the domain index directly, in the probabilistic version of our model, we will just predict both the mean and variance of the domain index. And this is where the MPN comes in, where we can use MPN as a probabilistic neural network to predict the mean and variance. And correspondingly, the loss we use for the discriminator will be a negative log likelihood corresponding to the Gaussian distribution. And we need to modify the encoder and predictor as well, of course. And our theoretical analysis actually shows that this probabilistic version of CIDA or p-CIDA can actually guarantee to match both the expectation and variance of the domain index. In terms of theoretical analysis, we show that these CIDA can be guaranteed to match the expectation of the domain index, and p-CIDA is guaranteed to match both the mean and variance of the domain index. And last but not least, we also show that the global optimal of the 2-player game between the encoder and discriminator actually matches the global optimal of the 3-player game between the encoder, predictor, and the discriminator. Basically, the third theorem says that if we train the encoder, the encoder, discriminator, and predictor jointly, we can simultaneously achieve perfect alignment and also accurate prediction for the labels. So to evaluate our methods, we have several baselines. We have at a single step categorical domain adaptation method like ADA and DNN, as we've shown before. And we also have multi-step categorical domain adaptation methods, CUA here. It's actually a simple way to augment the categorical domain adaptation so that this model can incrementally adapt domains one by one. Let's come back to the toy data set to see how they perform. We have let me remind you that we have 30 continuously indexed domains. We have red and blue as classification labels. And the first 6 domains is used as source domains and the rest as target domains. And this is the ground truth, and this is the result from the categorical domain methods, and this is the result for our SIDA. Let's take a look at CUA more closely. We can see that although CUA can capture the correct train of the decision boundary, but the boundary that it predicts is actually very rugged, and sometimes it might even be a little bit confusing. And in contrast, our model SIDA is able to get both the correct train and a very smooth decision boundary. Besides the first toy data set, let's take a look at another data set with a sinusoidal shape, where we have 12 continuously indexed domains. This is domain 1, domain 2, all the way to domain 6 and 12. And we're using the first 5 domains as source domain and the rest as target domains. And this is the result for the single step categorical domain adaptation. This is for CUA, and this is the result for SIDA. Again, let's take a closer look at CUA. We can see that CUA actually performs poorly in the domains inside this orange box, because basically this is because the CUA adapt incrementally from one domain to another. That means if it fails in some intermediate domain, it's going to cause catastrophic failure in all following domains. For example, CUA is going to adapt from domain 5 to domain 6, from domain 6 to domain 7, from 7 to 8, and from 8 to 9, and it fails catastrophically here, leading to poor performance in all following domains. And in contrast, our SIDA can successfully and simultaneously adapt across all domains. To evaluate our method also in the real-world medical scenario, we also consider the problem of sleep study at home, where the input are actually time series signals, one from nasal cannula and one from breathing bell. These are some multi-channel breathing signals. And we have a predictor, for example, a neural network, to predict one of the 4 classes of the sleep of this patient. One is awake, the other is REM and light sleep and deep sleep. We use 3 sleep study data sets, SHHS, MESR, and SOF. All these data sets contains subjects of different ages, and this age can be used as a continuous index for our model. And we consider 2 scenarios or settings for continuous domain adaptation. We consider domain extrapolation, where we use younger patients as source domain and older patients as target domain. We also consider domain interpolation, where we use younger and older patients as source domain and middle-aged patients as target domains. Here's the result for different methods. We can see that categorical domain adaptation barely improves the performance and may even hurt the performance sometimes. And our method, SIDA and p-SIDA, actually improve the performance in both settings, in both the extrapolation and interpolation settings. And interestingly, we can also see that the proposed SIDA method has larger performance gain in the extrapolation setting because it's more challenging, and therefore it can show more advantages of our model. Besides intra-data adaptation, we also consider cross-data adaptation. We can see that here, for different data sets, they actually have very different age distribution. And in particular, the SOF here, they mainly contain relatively older patients. And therefore, it's very difficult to adapt from SOF to other data sets with wider age range. And in this case, interestingly, PSIDA can significantly outperform the other methods here. So until now, we only consider continuously domain adaptation with a single domain index. But in the reality, we often know that there are multiple factors that can affect the domain shift. Therefore, here we introduce this idea of multi-dimensional domain index. So besides using age as a domain index, we also consider domain index like physical wellness. Intuitively, if you look at real-world data for two patients of the same age, usually the patient with better physical health will have better sleep quality, right? So it makes sense to use a higher dimensional domain index and include physical wellness as well. And besides these two, we also consider other domain index like emotional wellness. Like basically, we consider a total of 11 domain index in the model, including age, physical wellness, emotional wellness, fatigue level, and the other 7 index. And we show that in the experiments, multiple domain indexes can actually further improve the performance. So to summarize here, we actually identify the problem of continuously indexed domain adaptation and propose the first general domain adaptation method for this setting. And we have theoretical guarantees that SIDA can actually align continuously indexed domains at equilibrium. And we also show that probabilistic neural networks like NPN can be used as discriminators to further improve the adaptation performance. So with all this work, what we learn is that these probabilistic graphical models can use to formulate both the deep and graphical components in the Bayesian deep learning framework. And this Bayesian deep learning framework is suitable for any applications as long as it involves deep representation learning and complex conditional dependencies. And the bottleneck layer representation, like the X2 in the model, can serve as a bridge to marry these two components. And last but not least, tight two-way interaction is crucial for information and performance boost. So to conclude, basically here we have talked about a unified and principal model, what we call Bayesian deep learning, and we figure out how to develop and formulate both the feed-forward and recurrent version of the deep components for this framework. And we have the first hierarchical Bayesian model for deep hybrid recommender systems. We have the first deep learning model in the relational domain of graphs, and we also derive an efficient and lightweight Bayesian treatment for neural networks and Bayesian deep learning with some applications in healthcare.